There are 5 basic types of speed position sensors. The magnetic sensor, which produces a sine wave, the magnetoresistance sensor, which produces a square wave, the Hall effect, which also produces a square wave, the read type, which is oftentimes used on vehicle speed sensor applications, and finally the optical type position sensor. The magnetoresistive, Hall effect, and optical sensors need their own power and ground to operate. The optical sensor also uses a phototransistor to create this signal. The 2 most common types are the magnetic or permanent magnet sensor and the Hall effect position sensor. The magnetic sensor produces its own sine wave. Generally speaking, as seen here on screen, all speed position sensors are composed of the sensing tip or coil, the electrical connector socket, and a possible transistor housed inside the sensor casing itself. Magnetic sensors do not use an internal transistor. All position sensors are affected in one way or another by the air gap between the sensing tip and the reluctor or toothed wheel seen here on screen. The amplitude of a 2-wire magnetic sensor is directly affected by the air gap between the sensor and the reluctor wheel. The amplitude is also affected by the speed of rotation of the reluctor wheel. Magnetoresistive and Hall effect sensor amplitude is not affected by the speed of rotation of the reluctor or down ring. However, these 2 sensors are affected by the air gap between the sensor and the reluctor ring. A further consideration of magnetic sensors is the bias voltage provided by the ECM. These very low current bias voltage is used by the ECM to detect open and short circuit conditions. However, not all magnetic sensors used bias voltage use a voltmeter to verify whether a bias voltage is present. Hall effect sensors, which are very common, work by toggling or pulling a reference voltage to ground, thereby creating the square waveform. This reference voltage, to be toggled by the Hall effect speed sensor, is provided either by the ECM or the ignition control module, or ICM. Remember, the output of a Hall effect sensor, magnetoresistive sensor, or optical sensor is always a square wave. Hall effect and magnetoresistive speed position sensors employ an internal transistor to do the switching and be able to toggle the reference voltage to ground. These type of sensors are oftentimes used for cam and crank applications, and in modern systems also for wheel speed sensor applications. The signal path of a speed position sensor is extremely important during diagnostics. There are 2 basic ways to pass a signal along: point-to-point, and by using a vehicle module inter-network. With point-to-point connection, the speed sensor is directly connected to its own respective module. With a network system, the speed sensor is connected only to one of the modules, and such a module is in charge of broadcasting or passing along the speed and position information to the rest of the system module units. Network systems are very popular in newer systems due to the savings in weight and less complex electronics. As much as 200 pounds of weight in wires is saved by using a network system. This translates to a lighter and more fuel-efficient vehicle. Any direct aspect of speed sensor signals is the relationship between the cam and the crank sensor synchronization. Remember, when ascertaining a relationship between these 2 signals, there are always 2 crankshaft revolutions for 1 single camshaft revolution. These 2 signals have to match precisely. It is very common to see an engine that will not start due to a loss of synchronization between the camshaft and crankshaft. The end result will be an ECM cutting pulsation to the injectors in an effort to protect the engine from mechanical damage. It is useful to develop your own signal waveform library for later reference when diagnosing these systems.